Good morning. My name is Junfan. I work on robotics research and run Saturday Robotics, a Bay Area community bringing together researchers and founders and engineers working on embodied AI. Today's panel asks a practical question. Can AI actually rebuild American manufacturing? We have three panelists approaching this challenge from different angles across robotics, manufacturing, and AI. So quick 30-second intros. Who you are, what you are building, and the one bet your company is making that others can't.
Hi, I'm Lukas Pankau. I'm founder of Industrial Next. Over almost 2 decades in product development at Tesla, Waymo, and other companies, we just realized there was so much missing from the manufacturing industry and manufacturing technology, and that's what we're building in Industrial Next. Ultimately, the autonomous factory for producing whatever you need, wherever you need it. And one bet that we're making is fundamentally that everything on the production line needs to run on the edge without any cloud support whatsoever. And the models need to be fast and they need to be very precise. So it's a little bit different than the typical research lab physical AI approach.
Good morning, everyone. My name is Chris Chen, and I'm the global partner for Faraday Future Group. And I'm also serve as co-CEO of FFAI Robotics. So we are the US-based physical AI infrastructure company. We are the first US company who is able to deliver both humanoid and quadruped and mobile manipulator different forms robot starting from early this year. Glad to talk with you.
Morning, everybody. My name is Adarsh. I'm founder and CEO of Foundry Robotics. Been building robots my whole life. Started my career building robot dogs for the military. I was employee 4 at a company that did that, so I'm the guy that goes into the coal mines and puts really cool robots in really shitty places. Actually, I don't know if I'm supposed to say bad words. More recently, I was at Scale AI. I built and ran all of foundational robotics at scale, so all of the data that the physical intelligences of the world, the generalists of the world use, we have a bit of a hand in it. And then Foundry Robotics is actually an AI-first, assembly-focused, dual-use factory. We build factories from the ground up, and we happen to have a whole lot of robots in them. So excited to chit-chat.
Thank you for the intro. So the first question, everyone has impressive demos, one sentence each. What is still the hardest thing for a factory robot to reliably in a real production environment, not in a demo setting?
The hardest thing to this day is still managing change in any kind of factory setting. And if you've been in product development, I'm sure you know, people will change things and not tell you about it. But your production line needs to be able to cope with that.
I agree with Lukas because each factory has a different situation, different equipment, different people, different environment. So that's why the reliability is very important. So that's why we only focus on some certain skills like for example, loading and uploading and mobile handling and sorting. We are not trying to do everything in the factory. It's still in a very early stage. We have to educate the market and work with some integrators to deploy the robot into the factory.
I agree with what's been said. Let me make it a little bit more concrete. Managing change is a really great way of putting it. I think of it even more bluntly as like, how do we get really, really good at screw driving, right? Like, nobody thinks about something so tactical and concrete, but how do I deal with the fact that I need to go from an M4 to an M3, or it's a 20 millimeter bolt to a 25 millimeter bolt? My torque rating changed by 10%. Half the factories don't even do torque rating anymore unless you're literally at Tesla, and that's the only real factory that's scaled in the last 20 years in America anyways. So managing change at an extremely granular level is borderline impossible today.
Cool. My next question is for Adarsh. Foundry Robotics build and operate its own factories. What does owning a factory allow you to do that a robot vendor typically cannot?
This is, this is the thesis of the entirety of Foundry, right? So I'll talk about it in 2 ways. In a pre-physical AGI world, the most valuable asset to foundational robotics and manufacturing is a highly diverse data set. I know, because I helped invent the robotics data industry, there's not a whole lot of satellite building and robot dog building and battery building that goes into training the models just yet. So a company like ours becomes the single most exciting data set. In a post-physical AGI world, let's say I handed you the weights. What do you do with them? It's not the same as in language. Let's say I went to the future and I handed you the weights of like Gen 7 or Pi 8.6, right? You need an entire factory that's designed completely differently to be foundation model friendly. We have fiber lines going to all of our robots. We have GPUs under each cell. We have a server rack in the basement. Like the way you think about a foundation model enabled factory is nothing like anything that exists today. And so before the models become perfect, we're the single most valuable data set. After the models become perfect, we've already thought about what it takes to make them very, very useful and actually deploy them. So what building the factory from the ground up allows us to do is actually derive value from them.
Yeah, that definitely makes sense. And a follow-up for that is Foundry's moat the robotics foundation models or the manufacturing know-how? If a competitor had your models, could they reproduce Foundry?
Absolutely not. Our moat fundamentally comes from two things: data and manufacturing expertise. My co-founder ran the entire Model Y program at Tesla. Emmanuel Lamacchia is an absolute legend, best-selling car in the world, one of the largest, most successful assembly lines in America today. It is very rare to take that kind of expertise and understand how to distill it into the models. The way we think about it is, I don't pre-train my own model. I partner left, right, and center. The labs are much better at teaching the models the laws of physics than I am. But there's nobody better in the world at teaching the models the laws of manufacturing than I am after they've learned the laws of physics. So the fundamental belief is you can only get the t-shirt folding models to become satellite building models when you have the intelligence we have. And then once you have that model, the only way to derive value from it is to have a factory that's actually capable of deploying it. So in either world, it's us.
Yeah, thank you for the answer. Also, I had the pleasure to visit Foundry's office at your opening happy hour. Yeah, so my next question is for Lukas. So you started with electronics manufacturing, the tightest tolerance in the domain. Why lead with the hardest problem?
Honestly, we're masochists. When we've looked at the task required for manufacturing anything of any kind of value, right? Be this a car, be this consumer electronics, be it even any sort of defense equipment, right? We've done bin picking, for instance, 10 years ago at Tesla. It's been done before. Like there's not that much expertise required to make that work, right? And I say that also from a little bit of a privileged position, just because I've been there at the beginning of sort of when these things were invented, right? But the challenge is really, as sort of Adarsh mentioned, screw driving, right? A lot of the screws that we deal with, that are easy for robots to handle, are somewhere in the M4, M5, M6 range, right? But I have yet to see a solution that can reliably put in M.5 screws into something like a phone. And in fact, even on the assembly lines of Foxconn and whatnot, that step is still manual. It's not automated because there's no robot that can do it. And so being able to build that foundational technology that can handle these kinds of tasks lets us then scale much faster once we have these kinds of technologies.
Yes, that makes sense. And I noticed that your team says 2 hours of extremely high quality data beats months of mediocre data. And what's your opinion on data quality vs data scale?
So one of the trade-offs you have to make when you're running a model of a given size is that either you get the generalization or you get the precision. And if you're folding a t-shirt, missing on the precision a little bit is fine. You won't even notice it. The problem is if you're missing on precision and you're putting a tiny 0.5 millimeter wide FFC into a button assembly on a phone, you've broken the phone. Right? At a cycle time of 4 seconds or whatever per phone, if it takes your model or 10 minutes to continuously learn and adapt, like you've destroyed 100 phones, right? And the challenge there is that, or rather the limitation, sort of the boundary limitation, is that you can't go with current compute technology. You can't go almost infinite in size, right? Because your assembly line needs to work fast, which means you need to be able to do inference really quickly. And you need to be able to do inference at very low latency for that model to be useful. And so you're capped, in a way, at the maximum size of the model. And so you have to make that trade-off of, do you get precision or do you get massive generalization? And ultimately for us, that precision is just really important.
Yeah, thank you, Lucas. I think that's really some hot takes. And my next question is for Chris. Chris, you said that data, not algorithms, will define the next generation of physical AI. Unlike LLMs, robotics still lacks internet scale, diverse real-world interaction data. And factory data is expensive, proprietary, and every plant is different. Where do you see the real factory data come from, and who owns it?
Thanks for your question. I think we agree with that. We are doing the transition period from digital AI to physical AI. The real challenge is that the bottleneck will be data. So digital AI is easier to collect data because you can find a lot of data, tons of data from internet, audio, text, video, whatever you want. Internet existed there. But physical AI is way more complicated than digital AI. Actually, digital AI is language-based model. But physical AI is more complex. You cannot see any wording, picture written on the sky, on the wall, on the ground for you to reference. You have to build a real physical AI data collection ecosystem through the real robot collaboration. Now, no any golden rules for data collection. Somebody is doing simulation, somebody doing the egocentric, somebody is doing teleoperation. Nobody knows which one is the best way. But in my mind, I think the best way is the data should come from the real world deployment. Like us, we already deliver hundreds of units to the real customers, and each robot can generate data. And the data can make the robot better, can train the new model, and then to trigger more deployment. That's my logic. So regarding the factory, still we need to collect data through the deployment, work with the integrators, the manufacturing OEMs, and generate enough data to train the robot. So that's why I only focus on some single task. Like I mentioned, the machine tending, the machine, handling, and sorting, et cetera, et cetera. We don't want to, nobody can make a robot does everything. So we just focus on a single easier area to deploy. Yeah.
Impressive. And I'm curious on your opinion. Does robotics need a ImageNet moment first, or do we need millions of deployed robots first? Is this a chicken and egg problem?
Of course, that's going to be my answer is the millions robot deployment. So I think the future winner going to be have the mode will be the combination for four things for the manufacturing. First one is a very strong foundation model. Second one may be the manufacturing know-how, because that's a very specific expertise area, for manufacturing. Third one is the capability for the real-world deployment. And fourth one is data. So as long as we can deploy enough robots, then can make the capability of the robot better, and it can attract more factory to join the ecosystem. Now, a lot of factory, because we are discussing with the integrator of the manufacturing factories, they're still hesitating to apply the robot. But we need to prove that that's the best way to bring them to the next chapter for the manufacturing. Yeah.
Yeah, thank you, Chris. There's a lot of hot takes. And finally, the question for all. Everything we've discussed, reliability, factories, and data, comes down to scaling. In language models, we know the scaling law: more data, more compute. But in physical AI, there is no agreement. So pick one choice. Does physical AI scale primarily on A, fleet data, B, simulation, C, teleoperation, or D, manufacturing expertise? One pick.
If I were to pick out of that list, I would say manufacturing expertise, because that's the gateway to all the other parts that you need: the data, the quality, the processes, the ability to handle change. And sorry if I go a little bit over, but typically what you get is your models are only about 10, 15% of the entire solution, right? There's a lot more to building an AI-powered production line, as Adarsh sort of mentioned, than just having a good model. And that manufacturing know-how is what buys you everything.
I plus one to what Lucas said, right? Like, I think if you think about the bottleneck today, if you have a half-decent AI native factory, even if you haven't reached if you haven't saturated all the different technologies you can use, you start to build the system to build the AI-driven factory, right? Like, I think it's important to remember these things aren't you build it once and you snap your fingers and now you have an AI-driven factory and it's all magic, right? Like, you have to build the process and the underlying know-how to collect the data and then collect different kinds of data. Like, I think it was very accurately pointed out, there's no consensus in the ML paradigm in physical AI just yet. Some people say it's a special glove, some people say it's egocentric, some people say it's teleop, some people say it's a mixture. Nobody really knows yet, right? And given the complexity of deployment and given the lack of convergence in paradigm of training, not to use a lot of words, like that basically puts you in a place that the most valuable, lowest risk asset you can have as a company deploying robots in manufacturing is manufacturing know-how where people are rethinking how it should work. It is equally important to do physical AI for doing dexterous tasks as it is to build, and this is something our team is working on, an MES or factory operating system that treats robots, people, and agents all as first-class citizens. Those two things are equally important. They're equally valuable, right? So I think it's important to remember that like there's a big difference between a sack of robots and a t-shirt folding model and an excellent factory. Very, very different things.
I think it's not one or the other choice question. So I think egocentric is important, simulation world model is helpful, and the teleoperation is more accurate for training the robot. It's not one against each other. So I still want to say the biggest thing is that focusing on the building the physical AI infrastructure and focusing on the real world deployment. In our mind, I think when three things align, the skill will happen. First thing that we have to create the practical value. Second one is frequency usage, and third one is a clear ROI need to be delivered. When three things align, the skill will happen. More robots can be deployed, and more data can be generated, and the industry can be moving forward. Yeah.
Yeah.
I do want to call out, just none of us talked anything about sim, right? We all ignored option B. I think it's just worth, like, I think we should probably talk for like 10 seconds about why that's the case, right? Like, simulation always has a place in the robotic development stack, but like, you always end up in this place of like, is it cheaper to develop a simulation system that is complicated enough to do something really, really nuanced? Like, the example I use a lot is like, simulate a wet ping pong paddle. That's super weird, right? Like it's rubber and it's wet. What happens? Like put oil on a ping pong. What happens? It's super weird. It's actually just cheaper to get a bunch of guys to collect data on wet ping pong paddles. Like the amount of compute you'd need to run a simulation that does that right is absurd. And so, you know, people talk a lot about simulation. Maybe world models are. There's all this going on, and I'm generally excited about like smart people working on hard problems. That's like a universal statement, but like. In robotics, historically, it has been completely impossible to rely 100% on sim, right? Especially in something as dexterous and contact-rich as all the manufacturing tasks that all of us here on the panel work on.
Exactly, and one of the big things actually that you mentioned is, you know, in simulation, a lot of the contact dynamics and the physics of the objects are just not there. So dealing with anything that's deformable, like cables, connectors, harnesses, anything like that, is like, there's no amount of simulation that will give you that data for right now. At the same time, though, simulation is extremely important, I think, to continue doing research in, because that is really the only way that long-term you can scale this beyond, you know, maybe a factory or two. Simply because, you know, it is easy for right now to have, you know, 100 guys somewhere in a room collecting data on something, but you have ultimately a near infinite number of somethings that you need to collect, right? And so at some point you do hit that kind of scaling point.
I guess we have only 1 minute left, so one last question for Adarsh about continuous adaptation. Factories don't necessarily need infinite generalization. They need continuous adaptation. Which is harder, a robot that learns 1,000 tasks once, or a robot learns one new task every day without breaking yesterday's skills? Will continuous online adaptation be the real product or still in research?
It's definitely the second one, right? Learning more and more tasks is always harder. And I think what's sort of implicit in your question is the quality bar. It's not folding a t-shirt very badly. And as Lukas said, it's not building a broken phone and like doing a bunch of nonsense, but the phone doesn't work. It is like maintaining the quality bar of getting good at fastening, getting good at placement, getting good at snap fits, getting good at bearing presses, right? Like there's a very real binary quality bar in manufacturing. Does the thing you built work or not? Is it actually something that is usable, or is it a mediocre T-shirt full that's 4 times sped up on the internet? And so for me, given the importance of quality and given the importance of what I like to call like superhuman speed, like is replacing a human action with a model and a robot actually valuable because A, your error rate goes down, and B, your speed goes up. Those are really the only 2 metrics. Maintaining that bar for one task and then another task and then a third task is infinitely harder than doing a lot of tasks really poorly once. Like, that has no economic value.
Yeah, thank you everyone for your input. And one closing question, really quick. So 5 seconds each. Name one anti-consensus belief in the robotics industry.
Okay, I can go first. So the answer is simple. The future winner will be not the company who has the biggest, strongest model. I think that should be the company who's building the good physical AI infrastructure and the deployment capability.
I think the future ultimately belongs to, once we automate like the entire factory or whatnot, it's going to be way more boring than anything we can imagine right now. I think that's sort of where we're headed ultimately.
I agree. I was going to say what Chris said, so I'm going to come up with something that people who work with me know I feel very strongly about. But I think humanoids are ridiculously over-engineered. I think getting a humanoid to do your dishes basically means that dishwashers suck. Like, that's the very practical take. So I think they have a place. I think they're useful for complicated tasks where you need infinite dexterity because you don't know what situation you'll be in. Like if you're clearing a nuclear reactor, yes, send in the humanoids. If I'm doing the dishes, I don't know. I think we have other ways of doing it that make a little more sense.
Do we still have time, or we are at time? More minutes. Okay, more hot questions going forward. Yeah, Adarsh, you mentioned world models. So I have a question for maybe, it's optional for everyone. So many researchers believe the missing layer is a world model that understands physics, objects, and consequences. Do you think world models are the key layer that connects the simulation, data, and real-world deployment, or is the bottleneck somewhere else?
I can go first. So world models and then the general purpose robot, the general brain, etc. Those are the right direction, but that's the most difficult things that we can achieve the better result. So in my mind, that's good direction, but don't rely on things like that. We have to focus on the real, simple use case scenarios to deploy the robot.
So I maybe disagree a little bit there, because in a lot of these kinds of very contact-rich tasks, honestly, a world action model is really the only way we know, for instance, how to solve it. And that's, in fact, what we're actually deploying right now for assembling small FFCs. And just being able to predict that sort of physical state, even in latent space, is extremely valuable for the robot to be able to perform some of these more complicated tasks. So I think, I don't know if it's necessarily a missing layer, but I think it's going to be a very, very important ingredient.
Yeah, I would, I think I prefer Lukas's framing, right? Like, there's always a missing layer. After this one, there'll be something else, right? Like, that's just the existence of research, which is super reasonable. I think if I zoom out, what does a world model achieve that other perception approaches don't? There's some amount of physics awareness. There's some amount of force awareness, right? Like, it's very hard to imagine a world where physical AGI exists where you don't have awareness of the physics of the world around you, and you don't have awareness of your robot's own interaction with the world. And so if you believe that thesis, I think world models can be a useful tool, if they work and stuff. But in general, I think the direction that research will go is, how do you become more physics aware in different ways? Do you actually start incorporating force data from your end effectors, blah, blah, blah. I mean, there's all these different things we can open, but I think world models are probably the most hyped version today of generally physics-aware perception and force-aware perception. This is roughly the way I think about it. Is it that literal approach or others? I mean, the researchers will tell me.
Yeah, I have to clarify. Don't get me wrong. I'm not against the world model. I think we cannot just focus on one way to do things. We need to focus on the simulation world model and the real world deployment together. Yeah.
I love the spiciness. Our panelists disagree with each other and somewhat agree, but this makes the panel more interesting. So I guess we have only 1 minute left. So one final closing question about the reshoring. So robot intelligence, manufacturing know-how, labor, capital, supply chain, pick one thing that actually limiting US reshoring. Optional.
Right now, I think supply chain, honestly, in a lot of cases. I think it depends a little bit on the industry as well. I think you may have a slightly different take on that too. But typically in electronics and automotive where we play, it's typically the supply chain. A lot of processes and a lot of things today that go into our products, there's no knowledge of how to make them anymore in the US. Those processes, they're gone. And there's no one here left who knows how to do that. And so I think that's going to be a very big driver for reshoring.
I think what Lukas said makes sense, and he predicted that I was going to say something slightly different. We focus primarily on national security and critical infrastructure, things that need to be 100% built in the United States. And the way I think about what you just said is it a capital problem, a labor problem, a supply chain problem, or a know-how problem? Let's say I gave you infinite money. I gave you $100 billion, and I asked you for 10 million drones. You have no way to actually, there's nothing you can do. Let's say I gave you 1 million people, and I asked you for 10 million drones. There's still very little you could do. Let's say I gave you 10 million drones worth of parts that are designed poorly and have absolutely no DFM. It's still very unlikely you would return 10 million drones to me. So the way we think about this is like there's the ability in national security and other critical infrastructure to go from a world of building 10 highly bespoke and exquisite things to 10 million much more commoditized things. That know-how of mass producing complex electromechanical systems is completely non-existent. And so even if you gave a lot of money and a lot of people to a program trying to do that, there's no ability to coordinate that, right? Like, it's very easy when you don't have money and people to say, I just need more money and people. And then you have money and people, and then you realize coordinating the deployment of those resources is borderline impossible unless you've actually built out a structured, rigorous manufacturing program and know-how. So I strongly believe it's know-how.
Yeah, my answer is very simple. So 3 things really matter regarding the reshoring to make it happen. First thing is how to reduce the labor cost. Second one, how to improve all the automation in the factory. And third one is how to build the supply chain ecosystem, a local production for all the suppliers. That's the 3 challenges that we have to overcome.
Thank you very much. I think that concludes our panel, and I hope you enjoyed all the hot takes. And let's give a big round of applause to all our panelists. So I will give the stage to the host, and thank you very much for your attention.
Thank you.